So this is the spot where the recording got a little weird for the last lecture. So I'm going to just pick up and just kind of start over right here with the precipitation reactions. We already went through the solubility rules, and so now we want to go through some precipitation reactions and predict if, number one, we have a precipitation reaction, and number two, what the precipitate is going to be. And that's going to be based on our solubility rules. So I have three examples here. The first one is an aqueous solution of silver nitrate, and we're saying that that is allowed to react with an aqueous solution of sodium chloride. So this problem is telling you that both of these solutions are already where you already have compounds that are dissolved in water. So they are soluble. And you're going to basically pour one into the other or pour them together into an empty beaker or whatever. You're going to allow these solutions to intertwine. And all of these ions are going to be allowed to react. You need to predict your products, and you need to visit your solubility chart and predict which of these products is actually going to be insoluble. If you have one, then you have a precipitation reaction. That solid will be the precipitate. It will be the solid that precipitated from solution, the insoluble product. All right, so let's just draw what we have here based on what we've been told. An aqueous solution of silver nitrate. So we have silver, and these guys come together in a 1-to-1 mole ratio. They told us that it's aqueous, right? Silver plus 1, nitrate minus 1. We're allowing this to react with an aqueous solution of sodium chloride. So we know that these guys come together in a 1-to-1 mole ratio, sodium plus 1, chloride minus 1. We pour these two different mixtures together, and we're going to do a double replacement reaction, just like we talked about in chapter 7. We don't know if it's a precipitation reaction until we predict the products, and then we decide if they're soluble or if they're not. If they're not, then whatever is not soluble, whatever product that is, will be our precipitate. And then, yes, we can say we have a precipitation reaction. So if silver swaps partners and takes on chloride, and you look back at your solubility rules, right, you would see, you realize that chlorides are generally soluble until they're paired with silver, mercury, or lead ions. We have paired this up with a silver ion, so we expect this to be insoluble. So you put little s there. That right there is your precipitate. Or in other words, silver chloride has precipitated from solution. But that's not the only thing that's in the beaker. We have another compound, and so the metal will be sodium. Nitrate is the other ion. And this is going to be soluble. All nitrates are soluble, without exception, and all group 1 metals. So we have our precipitation reaction, yes, and our precipitate is going to be silver chloride. For the next one, we're allowing sodium sulfate, so it's an aqueous solution of sodium sulfate. Sodium forms the plus 1 cation. Sulfate has a -2 charge. So, and this is going to be aqueous, right? This is going to come together in a 2-to-1 mole ratio. 2 equivalents of the sodium ion for every 1 equivalent of sulfate. This is allowed to react with an aqueous solution of barium chloride. Barium's in group 2, takes on a +2 charge. Chloride is a halogen over in group 7, takes on a -1 charge, so we're going to need 2 of those. And these are both aqueous. And we're going to allow them to react, and when they do, we're going to form sodium. Now there's 2 equivalents of the sodium ion over there, right? And instead of the sulfate now, we're going to pair the sodium up with the chloride. But there's also 2 equivalents of the chloride anion on the other side. So I'm going to form 2 equivalents of sodium chloride. And it's a big 2 in this case because sodium takes on a positive 1 charge. Chloride has a negative 1 charge. And so they come together in a 1-to-1 ratio. But to balance the moles, right, we put a big 2 out front. This will be aqueous, right? Chlorides are generally soluble. Sodium, group 1 metals are always soluble, or generally soluble without exception, so that's usually an always soluble. And so that'll be aqueous. And then the other product we're going to get, we have another metal here, so barium. Barium is going to have a positive 2 charge. Sulfate has a negative 2 charge, so these are going to be 1-to-1. Now, if you were to look back at the table and you see that sulfates are generally soluble, and then there are a few exceptions. The exceptions are when they're bonded to or they're paired up with strontium, barium, lead, silver, or calcium. So we have a sulfate and it is paired up with barium, and so we expect that this is not going to be soluble. This will be our precipitate. In other words, we have a precipitation reaction. The last one tells us that we're going to pair up an aqueous solution of lead 2 nitrate. So now we know nitrate has a negative 1 charge, and they're telling us we have lead 2. That means we need 2 equivalents or 2 moles of the nitrate anion, right? So to balance this out, if we have lead 2, we need 2 equivalents of nitrate. And they told us it was aqueous. And to this, we're going to add an aqueous solution of ammonium acetate. The acetate anion, I'll put this up here in a different color. So this is going to be derived from acetic acid. And the acetate anion looks like this, right? An abbreviation that we can sometimes use for this is ACO. The acetyl group, this thing right here, AC, the acetyl group is this thing right here. Very often you'll see this written. Acetic acid will be ACOH, right? And the acetate anion is just ACO minus. This is just us being lazy. There's a lot of different shortcuts for some of these compounds. So I'm just going to pair this up now. Ammonium is ammonia that has picked up a hydrogen, right? So ammonium. And then when we pair it up with acetate, you say OAC, right? So that's ammonium acetate. Ammonium has a positive 1 charge. The acetate anion has a negative 1 charge, so they come together in a 1-to-1 ratio. And we're told this is aqueous. We know it's aqueous because all ammonium compounds and all acetate compounds are going to be generally soluble without exception. So now on the other side, we're going to swap partners and see what happens. We're going to get ammonium nitrate. Now, ammonium has a positive 1 charge. Nitrate has a negative 1 charge. So they're going to come together in a 1-to-1 ratio, mole ratio rate of ions. All nitrates and all ammonium compounds are going to be soluble without exception. So this will be aqueous. But it's not balanced because on the other side, I had to use 2 equivalents of nitrate to balance out the lead 2 plus. So I'm going to have to put a 2 in front here. I can't put a parentheses around the nitrate and put a 2 on the other side because that's saying the ammonium complex has a positive 2 charge. That's not correct. I need 2 equivalents of nitrate anion, but ammonium and nitrate come together in a 1-to-1 mole ratio. So that tells me then that I need to balance the ammonium species on the other side, on the reactant side. I'm going to need 2 of those. So I'll put a 2 out front there. But that's okay because acetate has a negative 1 charge, and I'm going to need 2 of those anyway to balance the lead 2, right? So over here, I can put the OAC in parentheses and put a 2 on the outside. Each of those acetate anions has a negative 1 charge. It's right there. So I'm going to use 2 of them to balance out the lead. Now, All acetates are also soluble without exception. So in this particular case, all of the ions are in solution. So there is no precipitate, and so there's no precipitation reaction. So why do we care about this? Well, sometimes you can do a qualitative analysis test, and you can even quantify this if you like, where if you're hoping for a precipitate, it's generally you're looking for a specific ion. Like if I want to test for sulfate in seawater, I can set this up, right? Where I can stick some sodium sulfate into a beaker, an aqueous solution, and grab some seawater, right? Or grab some seawater and stick some barium chloride into a beaker, right? And add a little bit of acid. Usually you need a little acid for this. And if I form a precipitate and I know what the other compound is, and I know that it's soluble, and I know that barium sulfate is not, then at the very least, there is some sulfate in solution. And so we can ask ourselves to do some calculations, some stoichiometric calculations based on knowing, number one, if we have a precipitation reaction, number two, how much of a solution we're going to need to precipitate a certain amount of one of the ions, if we know what that ion is going to be involved in the product. But knowing that you have a precipitation reaction in the first place is going to be key. And the other piece that's going to be pretty handy in some cases is if you really kind of only are interested in the precipitate. So if you know you have a precipitation reaction, and you want to remove all of the spectator ions because they're just sort of in the way. I mean, they're just going to be in solution, right? If you're focused on the solid, you kind of want to look at the business end of the precipitation reaction. And that's when we write out our net ionic equation. You want to start with an actual reaction equation, so a balanced reaction equation. And then you're going to write out your total reaction equation. And what that means is you're going to split up all of the ions that are in the aqueous phase and list them separately. So we're looking at just what's actually happening all together with all of the ions in solution. And we're also going to include the precipitate, right? But you don't split those up because it's a solid. It's not an aqueous solution of those ions. What do I mean? Well, let's start with the first one. We've got lead 2 nitrate, and that's going to be allowed to react with potassium sulfide, both aqueous, right? Both of those are aqueous solutions of those ions. When they come together, they're going to form 2 equivalents of potassium nitrate, also aqueous. And then our precipitate is lead 2 sulfide, and that is a solid. So what I'm going to do is I'm going to break up all of the ions. So in lead 2 nitrate, I actually have lead 2 plus, and that's aqueous. So if the lead 2 nitrate is aqueous, right, effectively what I have are these ions in the aqueous phase. So there's 2 moles of nitrate. So that's my first reactant there in the reaction equation, split up, right, into their ions in solution. The other reactant I have is potassium sulfide. And there's a K2 there, means I have 2 K plus 1 aqueous. And I have sulfide, -2. These are going to react. And we're going to form 2 moles of potassium nitrate, but it's in the aqueous phase. So I effectively have 2 moles of the potassium ion in the aqueous phase and 2 moles of the nitrate anion in the aqueous phase. And then I have my solid. I can't break that up because it's not soluble. What you want to do to write the net ionic equation is to look on both sides of the reaction equation and see if you spot some stuff that looks exactly the same on the left as it does on the right. For example, if I look on the left and I see I've got lead 2 plus, I look over on the product side, I don't see lead 2 plus anywhere. I see lead 2 sulfide, but that is not lead 2 plus in the aqueous phase. So that I'm going to leave alone. The other thing I see is I've got 2 equivalents of the nitrate anion on the reactant side. And I look on the product side and I see 2 equivalents of the nitrate anion. So those are spectating, right? It's hanging out in solution on the left and it's hanging out in solution on the right. So we're going to cross those off. It is a spectator ion. When I look on the reactant side now, again, I see two equivalents of the potassium cation. And on the product side, I see two equivalents of the potassium cation. Again, floating around in solution on the left, floating around in solution on the right, just spectating, not participating in the precipitation reaction. The last ion I see on the reactant side is sulfide, but I don't see any sulfide on the product side. It's tied up in the precipitate. So what I have here is the lead 2 plus cation on the reactant side. I've got the sulfide ion on the reactant side, and then I have the solid that those two formed on the product side. So the net ionic equation is simply going to be whatever is left over on the reactant side that we didn't cross off, so not the spectator ions, right? The ions that took part in the precipitation reaction are these guys. And what did they make? They made the precipitate, or the insoluble solid. That is the net ionic equation. This is useful for us when we want to look at the mole ratio, right, of the ions relative to the precipitate that is formed. When we get into a calculation, a stoichiometric calculation for a reaction like this is going to actually be helpful for us. Let's try one more. I've got copper 2 sulfate, an aqueous solution of copper 2 sulfate, two equivalents of sodium hydroxide in the aqueous phase. So these two aqueous solutions are going to be poured together. They're going to be allowed to react, and I'm going to form sodium sulfate as a product, and that's going to be in the aqueous phase, right? So that's going to be a soluble compound. And then we're forming copper 2 hydroxide. Copper 2 hydroxide is not soluble, so we have a little S next to that, right? That's our solid, our insoluble solid, otherwise known as our precipitate. I want to write out the entire reaction equation, so I'm going to break up all of the species on the reactant side, and I'm going to break up all of the species on the product side that are in the aqueous phase, right? We can't break up the solid because it's insoluble. So all of the species on the reactant side are in the aqueous phase, so we're breaking those up. I know I have copper 2 plus because sulfate has a -2 charge, and they are in a 1-to-1 mole ratio according to my reaction equation. For my other compound, I've got two equivalents of sodium hydroxide in the aqueous phase. When this dissociates, I will have two equivalents, or 2 moles, of the sodium ion in the aqueous phase, as well as 2 moles, or 2 equivalents of hydroxide in the aqueous phase. On the product side, I have sodium sulfate. Well, sodium has a +1 charge, sulfate has a -2, so it's a 2-to-1 mole ratio. So I have 2 moles of the sodium ion, 1 mole of sulfate, and then I have my precipitate, and I can't break that up because it's not soluble. Now again, I'm going to look on either side, and I'm going to pick out the ones that I see on the reactant side that look just like the ones I see, the ions, on the product side, right? I see copper 2 plus in the aqueous phase on the reactant side. I do not see that on the product side. I see the copper, but it's tied up in the precipitate, so we're going to leave that alone. I see sulfate in the aqueous phase on both sides of the reaction equation, which means the sulfate is floating around on the reactant side, and it is just floating around in solution on the product side. It is a spectator ion, so I'm going to cross that off. I see 2 equivalents of the sodium ion on both sides, spectator ion, I'm going to cross that off. And I see 2 equivalents of hydroxide on the reactant side, but on the product side it's tied up in the precipitate, so we're not crossing that off. We identify the ions on the reactant side that are not spectating, they are participating in the precipitation reaction. And so I can now write the net ionic equation. Copper 2 plus in the aqueous phase on the reactant side is allowed to react with 2 equivalents or 2 moles of hydroxide on the reactant side here. On the product side, we have our precipitate. And that is the net ionic equation. So why do we care to do these, right? Why are we writing that out? Well, it's a little bit simpler. You can see how the total equation is much longer and more involved, but not all of those species are taking part in the precipitation reaction. Why do we care who's taking part in the precipitation reaction? Well, if we have a problem where we're asked, for example, for the volume of a specific solution with known concentration, like how much of this stuff are you going to use, right? We already have the salt dissolved. We have the concentration. How much of that are you going to pour into a sample, right, of some other salt where I can precipitate a known quantity of the hydroxide anion? The hydroxide anion is in that other salt, and they give us the mass. So they tell us that we have 2 grams of potassium hydroxide in this particular example I have. 2 grams of potassium hydroxide, we are assuming it completely dissociates, right? And so really what we want to know is how many moles of hydroxide are associated with 2 grams of that stuff. So they then go ahead and tell us that the concentration of the other solution in the aqueous phase, right, that's going to be poured in, is 0.150 molar. It means that 0.150 moles of, in this case, ferric chloride, so iron 3 chloride, right, are going to be poured into a solution of potassium hydroxide where we have actually used 2 grams of solid potassium hydroxide in order to make the sample. So we have our potassium hydroxide, 2 grams of it, dissolved in enough water, right? They don't give us the concentration of that. They're basically asking the volume of the ferric chloride necessary to precipitate all of the hydroxide. You have to just assume that all of the potassium hydroxide will dissociate. And that's fine, right now. In Chem 32, you can calculate, actually, how much of that you expect to dissolve. But for now, we're just going to write out, first of all, our total equation. So our total balanced equation is going to be where we have our ferric chloride, and this is aqueous, and we're going to allow this to react with potassium hydroxide. On the other side, what we're going to get is, now I have the ferric ion, and I know that hydroxide has a -1 charge, so I'm going to need 3 hydroxides to balance out that ferric ion. And if we're precipitating all of the hydroxide anion, they're telling us essentially that ferric hydroxide is not soluble. The other species in the pot will be the potassium and the chloride. And those come together in a 1-to-1 mole ratio. And so I'm going to have to balance this out because I see on the other side that I have 3 chloride, and this will be aqueous. If I have 3 chloride on the other side, I'm going to need 3 chloride on this side. But if I go ahead and do that, then I have to balance the potassium. And this is going to be handy because I need 3 hydroxide anyway. So I'll put a 3 in front of the potassium hydroxide. And now I have a balanced total reaction equation. What might be nice is to write just the net ionic equation. I notice that on the reactant side, I have ferric chloride and potassium hydroxide, and they're both in the aqueous phase. And on the product side, I have ferric hydroxide, and that's the precipitate, and I've got potassium chloride in the aqueous phase. Well, if I have potassium chloride in the aqueous phase, then the potassium and the chloride, right, on the other side, the ions on the other side are spectating. So that means that if I look at the solid there, I see ferric hydroxide. The ions responsible for forming that solid are not spectating, they're participating in the precipitation reaction. And so in my net ionic equation, I will have the ferric ion in the aqueous phase. And the source of that ferric ion is this right here. They give us the concentration of this. This is going to be a big deal for us in this calculation. This is going to react with 3 moles of the hydroxide anion in the aqueous phase. That's going to be a big deal for us because we now have the mole ratio of the iron 3+ to the hydroxide anion. And it's going to make the salt that crashes out of solution, or in other words, the precipitate. When we precipitate the hydroxide from potassium hydroxide in that reaction, it's going to precipitate as ferric hydroxide. That's what that's telling us. So this right here is going to be our net ionic equation. And we're going to use these mole ratios, right, to solve this problem. What do we know? Well, they tell us that we've got 2 grams of potassium hydroxide. And that's great, but that does not tell us how many moles of hydroxide we have. Lucky for us, we can figure that out because we know that every mole of potassium hydroxide has 1 mole of hydroxide anion. So the first thing we want to do is turn these grams into moles. I know that 1 mole of this salt, potassium hydroxide, has a molar mass of 56.11 grams. So now I know how many moles of potassium hydroxide are in 2 grams. And I also know that 1 mole of this salt, potassium hydroxide, has 1 mole of hydroxide anion. Now I know how many moles of hydroxide are in a 2-gram sample of potassium hydroxide. So what's going on here? My grams of potassium hydroxide are going to go away. Moles of potassium hydroxide are going to go away. And I'm left with just moles of hydroxide. Those moles of hydroxide are going to react. See the net ionic equation there? 3 moles of those things. 3 moles of hydroxide are going to react, are needed to react with 1 mole of the ferric ion. This is from our net ionic equation. Now the moles of hydroxide are going to cancel out, and I'm left with the number of moles of the ferric ion I need to precipitate 2 grams of the hydroxide anion. In other words, I should say, a certain number of moles of hydroxide anion from 2 grams of potassium hydroxide, because they don't have the same molecular weight. But in other words, right now I know how many moles of the ferric ion I need. And what is the source of my ferric ion? It's going to be the ferric chloride, right? That's the solution that they're giving us, and they gave us the concentration. I know if I look at that particular ionic compound, that 1 mole of the ferric ion corresponds to 1 mole of ferric chloride. That is the solution I'm going to use to coax the hydroxide ion out of solution and form the precipitate. And then they tell us that 0.150 moles of this salt are dissolved in a liter of the solution. And that's from the concentration that they gave us. If you do this out, see now, go back over here, moles of the ferric ion are going to go away, moles of the salt are going to go away, and I'm left with just the volume of the ferric chloride solution that I need to precipitate the hydroxide anion. and it's going to work out to be 0.0792 liters, or more conveniently, 79.2 milliliters, and that will be ferric chloride solution with that particular concentration. So in other words, I need 79.2 milliliters of a 0.150 molar ferric chloride solution to precipitate all of the hydroxide present in a 2-gram sample of potassium hydroxide. And we used our net ionic equation as well as our total equation to solve this problem. So this is an example of what you can do, right, with your net ionic equation. Doing a calculation, a stoichiometric calculation, something that might be valuable to you in the lab with a precipitation reaction. So I want to now move into a different type of reaction. We were doing reaction types in Chapter 7, and I said to you guys, we're going to focus on 3 different types of reactions in Chapter 8. We're going to focus on precipitation reactions, acid-base reactions, and then we're also going to focus on redox reactions. So the next reaction that I want to focus on is the acid-base reactions. And so acid-base chemistry is where we're going to go next. And it might be nice if we defined what an acid was and defined what a base was. We're going to focus in this chapter mostly on acids, but I do want to introduce you to bases. And there's a couple of different ways that we can look at this. We've got a couple of different definitions anyways. For our acids, we have the Arrhenius definition. And you'll find that they're kind of similar, but just different enough where it's going to matter to us that we actually draw out an example for each. This is just basically creating H+. It's a source of a proton in solution. Right? That's going to be our Arrhenius definition. And an example of this would be simply just saying, I've got a source of a proton, right? So there's hydrogen bromide, but when it's in an aqueous solution, it is hydrobromic acid. And what do I get? Well, H+ in the aqueous phase and Br-. Right, so I got a proton in the aqueous phase, and I've got the bromide anion. So this is our Arrhenius definition of an acid. This is going to dissociate and just give us basically a source of H+. We have another way of looking at this, and it's the Bronsted-Lowry definition. And the way they look at it is that an acid, a Bronsted-Lowry acid, is a proton donor. Arrhenius looks at what's being formed in solution. Bronsted-Lowry is like, okay, how are we doing that? So in other words, we can say hydrogen chloride in the gas phase is bubbled through some water. And what we end up doing is protonating the water, right? The hydrogen chloride has a dipole moment. The hydrogen has a partial positive charge. Water, right, the oxygen on water has 2 lone pairs of electrons. And so that partially positive hydrogen is going to be taken off of HCl and put onto water to create protonated water, otherwise known as the hydronium ion. And what's left is the conjugate base of the acid, also in the aqueous phase. You could have said the same thing about HBr, right? If that's going to protonate some water, you get the hydronium ion. You can look at it either way. We're either creating a source of H+, or if we look at it from the Bronsted-Lowry perspective, we're saying that HCl in water is a proton donor. We can define bases much in the same way, right? So we have the Arrhenius definition of a base. And this basically is just creating the hydroxide anion in solution. Like, for example, if I were to take sodium hydroxide and just allowing this to dissociate, and there's the hydroxide. Bronsted-Lowry looks at it just a little bit differently and says, this is actually going to be a proton acceptor. Where the Bronsted-Lowry acid was a proton donor, this is just going to be a proton acceptor. How is it doing that? Well, it generally has a lone pair of electrons, right? Bronsted-Lowry base, and it's going to take on a proton. For example, ammonia. So the nitrogen has a lone pair of electrons. Water has a couple of protons that ammonia can take off. And actually, let me redraw the arrow here. This is a weak base. So this is kind of a back and forth thing. At equilibrium, you have every shot finding a little bit of ammonia in the gas phase. And some ammonium hydroxide in the aqueous phase. When you go out to the store and you buy a jug of ammonia for cleaning purposes, it's a liquid, right? You got a jug of something. So it's ammonia bubbled through water, right? And so there's this equilibrium going on here, this dynamic equilibrium where ammonia is not a terribly strong base, but it can depronate water a little bit all the same. So at some point, you'll find some ammonium hydroxide in solution, and when you open up the jar, when you open up the jug, you can smell ammonia. That's ammonia in the gas phase. So, but the ammonia itself is a Bronsted-Lowry base. It's a proton acceptor. It accepted a proton from water. So let's move on and just talk a little bit about the different types of acids. Chapter 8 focuses on protic acids. And so we're going to start out with number 1, our monoprotic acid. And this is going to be an acid that donates a single proton. So for example, like HCl, I'm going to put that into some water and protonate the water. But we've effectively donated one proton, and it was this one right here. That is a monoprotic acid. One proton. There are other acids out there that have the ability to donate more than one proton, right? For example, sulfuric acid, H2SO4. And you're going to remove one proton at a time. So this is going to be H3O plus. And then the conjugate base, after you take just one proton away, is going to be HSO4 minus. I took one single proton away, right? I can take HSO4 minus, theoretically, and I can do this again, and I get the sulfate anion. When you guys get into acid-base chemistry in Chem 32, you're going to find out that that second piece there is pretty unlikely to happen. When you get a really strong acid like that, its conjugate base is going to be pretty weak. And so the dissociation of that second acidic hydrogen is not nearly as awesome as the first one was. But just to give you an idea, poly here means more than one, right? So many. So in this case, we just did a whopping 2, but phosphoric acid is a source of 3 protons. So that's a triprotic acid. This is actually a diprotic acid. Your book focuses on monoprotic and polyprotic. Monoprotic means we're just giving up 1 proton, and polyprotic is, well, more than one. So how do we name these things? So there's 2 different types that we're going to focus on in this chapter. So for the acid, nomenclature means naming, right? So I've got some examples down here of binary acids. Binary acids are just basically an acid that's made up of an acidic hydrogen, right? So it's going to be something that this hydrogen is involved in a polar covalent bond with some other anion, and that anion cannot be oxygen for these binary acids, because oxyacids are their own category. We'll get to those in a sec. But some of these that you may have heard of, some examples, HF, HI, HCl, HBr, we have to name these things. How do we name a binary acid? Well, the first thing we're going to do is we're going to start out with the prefix hydro. And then what you're going to do is you're going to give the base name of the non-metal. So in this particular case over here, HF, I'm going to start with hydro. The base name of the non-metal, instead of fluorine, it would be fluor, right? And then I'm going to add ic to it. So fluoric. And then a separate word here is just going to be acid. So down the bottom there, HI, hydro. That's iodine, right? But it would be iodo, because it's not iodine anymore. So it'd be iodic. So iodic acid. Come over here, I've got HCl, so hydro. Notice how none of these have oxygen in them. And this would be chloric. And then acid. Last one, hydrobromic acid. So none of these have oxygen. They are all binary acids, right? There's 2 components. There's an acidic hydrogen and some other anion, but it's not an oxygen. So what happens when they do have an oxygen? All right, so we have a separate category. And there's 2 different ways to name these. So just like with our polyatomic anions, the oxyanions have their own nomenclature, remember? So we were going through and we've got suffixes that help us to differentiate the acids or the anions, right, with the greater number of oxygens. And we've got suffixes that help us to differentiate the acid or the oxyacid or the oxyanion with the smaller number of oxygen. So for example, we're going to start out with HNO3. HNO3, we're going to take the base name of the oxyanion, and then we're just going to add ic to it, right? So this was a nitrate, so NO3 minus was nitrate, but instead of 8, the suffix now is going to be ic if it's got a larger number or the greater number of oxygen atoms. So this would be nitric, and then acid. If it had the smaller number of oxygen, right? Like, remember when we had nitrate versus nitrite? So we'll come over here, HNO2. Instead of nitric acid, this is nitrous acid. Ic and us are not oxygen specific, right? We did the same thing with the transition metals. The larger of the 2 charges that are possible would have the ic suffix, and the smaller of the 2 possible charges would have the us suffix. So this is not oxygen specific. This is just, the amount of. So what is this next one? This one right here, HClO3. This was one of those ones where, remember when we had like those 4 different possible anions, right? We had perchlorate, we had chlorate, we had chlorite, and then we had hypochlorite, right? So this ClO3 minus was chlorate. So this would be chloric acid. Over here, if this was chlorite, this is chlorous acid. Can we have HClO4? Yup. It's actually one of the very few acids, otherwise known as superacids. One of the 5, I think there are 5 or 6 of the strongest acids known. Perchloric acid, that was HClO4, would be one of those. All right, so we just did, this one is sulfuric acid. SO4 minus was sulfate, right? So it has the larger of the 2 possible numbers of oxygens there. And so we're going to take the base name of the oxyanion and we're just going to swap out the suffix for an ic. So sulfuric acid. So then this one must be sulfurous acid. Last example, this was phosphate. So now it's phosphoric acid. And phosphorus acid. That's not a typo. There are 3 hydrogens in both of those. Yes. The structure is a little weird for phosphorus acid. But all of those hydrogens would be considered acidic. So let's move on and start discussing acid-base reactions. So we already talked about the fact that, and we're probably going to stick to Bronsted-Lowry definitions if you were wondering. I mean, you can look at it either way. It's a source of a proton or it's a proton donor, right? If it's an acid, it's going to generate, the hydroxide anion in solution, or it's going to be a proton acceptor. I prefer Bronsted-Lowry because not all bases generate hydroxide in solution, because you can do acid-base chemistry in organic chemistry where we keep water out of our reactions. So I prefer to use the Bronsted-Lowry definition. We're simply going to be talking about an acid being a proton donor and a base being a proton acceptor. And so we're going to move through and give a few examples of some acid-base reactions. I've got strong acids and I've got some weak acids to share with you guys. So an example of a strong acid-base reaction equation, and by strong, so I'm going to leave sort of the details of this for Chem 32 because you do a lot of acid-base chemistry in Chem 32. But suffice it to say for our purposes that a strong acid or base is going to dissociate completely, right? Which means, like, if I were to put some sodium hydroxide into a beaker and, add some water to it, I'd expect that the sodium and the hydroxide ions would dissociate from one another completely. But if I had some sort of weak base or weak acid and I were to add it to water, then some of it is going to dissociate and some of it isn't. Right? So that's sort of kind of, I guess, how we're viewing this. I'm going to pick a really strong acid now. Hydroiodic acid, HI. Right? And so how do I know that's really strong in the first place? If you really want to think about this, think about the strength and the length of that HI bond. Iodine, if you go down the halogens, right? We start up there at fluorine, then chlorine, then bromine, then iodine, and we're adding fluff to this as we go, right, all the way down. So the atomic radius of iodine is going to be significantly larger, say, than that of fluorine, which means that the length of that bond, right, that HI bond, is going to be longer than the HF bond. And if the bond is longer, it's weaker. And if the bond is weaker, it's easier to break. So when I put HI into water, I expect it to dissociate more readily than HF. The bond energy is weaker, right? It's longer, it's less strong. So I expect HI to dissociate completely. I'm going to allow this to react with a strong base, and strong base are group 1 hydroxides are a safe bet. So these guys are going to be in solution. And then what I'm going to get on the other side is essentially water and some salt, right? These little ions. But it's in the aqueous phase. So what do I have here? I've got a strong acid, it completely dissociates. I've got a strong base. On the other side, I'm making water and the salt corresponding to those ions. So the total equation for this, for our strong acid-base reaction equation, again, I'm just going to break up all the players here. I've got what? A source of a proton, aqueous. I have the iodide, anion, also in solution. I got a strong base, so that's going to completely dissociate. So potassium, aqueous, hydroxide, aqueous. And on the other side, what do I have? Water in the liquid phase. And I've got the potassium ion in solution and the iodide anion in solution. So effectively, I've got, let's see, on both sides of the equation, I've got some spectators, right? I've got the iodide anion, I've got potassium. And so my net ionic equation here for my strong acid-base reaction is going to be the proton source. This is what I care about. What did I make? I made something that wasn't an ion in solution. How did I do it? These two things came together. Same cannot be said for a weak acid-base reaction, because the acid, if it's weak, it does not completely dissociate. If I use a strong base with that, and that strong base does dissociate completely, then I end up with, say for example, we'll take HF because we just used that as an example. So this will be my weak acid. We have this in the aqueous phase, but it's weak, right? So this doesn't dissociate completely. This is my weak acid. So some of it will stay as HF and some of it will dissociate into H plus and F minus. I am going to use just the same base here. So that will completely dissociate. And what I end up getting is some water, because that KOH is going to completely dissociate, and a little bit of the salt. But the thing is, if the weak acid doesn't dissociate completely, right, then in the net ionic equation, my spectators are going to go away. I'll just leave those out. And I end up with HF, because not all of it dissociated. I have removed my potassium spectators. So I just have hydroxide there. That's the business end of that base. What did I make? Water. And F minus, because again, we got rid of our spectators. The only spectators were the potassium, right? Not all of the HF dissociated, the hydrofluoric acid. So a little bit of that is going to be in the pot. This will be important information for you to realize in Chem 32 when you go to do calculations. Acid-base reaction calculations, as well as titrations, which is not specific to acid-base chemistry. We can titrate anything really, but very often you'll do a titration calculation with an acid and a base. And speaking of titrations, what am I talking about? So a titration reaction is simply just, you're basically taking either a solution where you know the concentration of that solution and you're allowing it to react with another solution of an unknown concentration where both volumes are known, right? So, 1.0 molar of A, and you know that you used 50 milliliters of it, and question mark in terms of concentration of B, where you know that you used 20 milliliters of it, right? We're going to allow those to come together. And if we know the reaction equation, then we can actually calculate the unknown concentration. So whatever B was, right? If you know what the mole ratio of your balanced chemical equation is, then you know how many moles of B reacted with how many moles of A. And if you happen to know the concentration of one of those species, then you know, right, how many moles you should have had per unit volume of your other sample. So I have a little picture down here, and in the lab, your titration reaction looks a little bit like this. If you're doing an acid-base titration. What you're looking at on the left-hand side is an Erlenmeyer flask, and in that Erlenmeyer flask, the one that I've chosen to use anyways, is your acid. So down here, we have our acid, and you can see that, right, because they have H+ written here. So at the beginning of the titration, we have our acid in the flask. The base is up here in the burette. See this OH-? You have a solution of usually sodium hydroxide, potassium hydroxide, but you have your base. And you're going to open the stopcock. So this thing right here is the stopcock. You're going to turn that so that it's parallel, right? So right now it's perpendicular to the burette. It's going to be parallel to the burette, and you're going to open this up, and this is going to come down here. The base is going to enter, right? So you have your base in solution. That's going to enter the Erlenmeyer flask, and it's going to react with the acid. So in the reaction equation that they have shown you, it's really just the net ionic equation. H+ from the acid is going to react with the hydroxide anion from the base, and you're going to make some water. How do you know when to stop? That's this pink stuff. So they're going to add some sort of indicator, a couple of drops of indicator that reacts at in a certain pH range. You know to stop when that pink color persists. So see how it's turning a little pink in here? See right where they added that? That's right at that spot, right? The moles of acid equal the moles of base. In other words, we've neutralized the acid with the base right at that spot. But if you were to pick up the Erlenmeyer flask and swirl it around, right in the middle of the titration, like you're not done yet, so we still have a lopsided number of moles of each, that pink color would disappear. You'd see it, and then you'd swirl it, and it would disappear. Well, at the end of the titration, like the spot where you're supposed to stop adding the base, turn off the stopcock, you would swirl that reaction mixture, and that pink color would persist. And that means that your solution, the whole solution, after you've homogenized it, has equal numbers of moles of acid and base in it. So what you really need to know is what acid are you using, what base are you using, and if I don't know the concentration of one of these things, then I really hope that I have the concentration of the other, because I'm going to know how much acid I started with, and I'm going to know how much base I used to reach the end point. So I know the volume of each, right? And then I can calculate the unknown concentration. So that's what we're going to do in this particular calculation down here. We got a problem that says the titration of a 25.00 milliliter sample of a hydrochloric acid solution is of unknown concentration. So you don't know what the concentration of your acid sample is, but you know the volume. It's going to require 22.5 milliliters of base, and they give you the concentration of the base, 0.105 molar sodium hydroxide solution. And that's going to be required to reach the equivalence point, meaning stop the titration, we now have equal number of moles of acid and base in the flask, right? And then they say, what's the concentration of the acid solution? So I know the volume of the acid solution. I don't know the concentration. I do know how much base was required to neutralize it, and I know the concentration of the base. So if I start out with a balanced chemical equation, so for this, I'm going to write out HCl plus sodium hydroxide is going to give me sodium chloride and water. But we know that this is all aqueous. And this is a liquid. So if we got a strong acid and a strong base here, I know that this is going to be sodium plus 1 on this side, sodium plus 1 on that side, chloride minus 1 on this side, chloride minus 1 on that side. And then the only other ions that don't cancel out are going to be the proton and the hydroxide anion. So my net ionic equation would look like this, just kind of like what they just had in the picture up there. This is effectively what's going on in the reaction flask. So I can refer to HCl as H plus. I can refer to OH minus, right? I can refer to the sodium hydroxide as OH minus. So that's going to be helpful in my calculation. And you'll see it'll cut down on the number of mole ratio steps that you have to put into your dimensional analysis. So I'm going to start out with what I know. I know I have 22.50 milliliters effectively of hydroxide, right? And I know what the concentration is, but it's in it's molarity, right? So it's moles per liter. So I need to put this, it's 1,000 milliliters in a liter. And then I know the concentration. I know that there's 0.105 moles of hydroxide in a liter of the solution that I actually used. But I didn't use a liter, I only used 22.5 milliliters. So that's where we're at right now. If you only use 22.5 milliliters of this particular solution with that concentration, this calculation right here tells you how many moles of hydroxide you actually added to the flask of acid. Then you have to figure out, based on your net ionic equation there, how many moles of acid were quenched by the base, or neutralized by the base, right? So I've got 1 mole of hydroxide based on my net ionic equation. Mole ratio is 1 to 1. So it takes 1 mole of hydroxide to neutralize 1 mole of that particular acid. It's a monoprotic acid. And then, if I want to know what the concentration of the acid is, because if I were to stop the calculation here, check this out. Let me cross these out for you. Milliliters of, well, milliliters in general are being dividing to 1 there. Here's the volume, right? That's actually canceling out there. And then my moles of hydroxide are going to go away. The concentration is in moles per liter. I happen to know the volume, but it's given in milliliters, right, of H plus. But molarity is not moles per milliliter, it's moles per liter. So 1,000 milliliters to convert to liters. So when I cross out these units, milliliters are going to go away. And what am I left with? I'm left with moles of H plus per liter. And that is a concentration unit. So what did I get? I got 0.0945 molar, and that is my HCl solution. So they asked me for the concentration of the acid solution, and that was the acid that was hanging out in the flask underneath the burette. I squirted 22.5 milliliters of a 0.105 molar sodium hydroxide solution into a flask that had 25 milliliters of acid. We just calculated the concentration of the acid that was actually in the flask. So that's how you would do a titration calculation. In the next lecture, I think I'll probably break the next one into a couple of lectures. So instead of just lecture 3 or 4, whatever number we're on at this point, I don't know. I've got 2 more reactions I'd like to cover. And the next one that I'd like to cover is sort of a nice segue out of acid-base chemistry. We'll do gas evolving reactions, and then we'll do redox reactions. We covered redox reactions, what they actually are, in chapter 7. So I'll just give you some specific examples of that in the next video.